So previously we talked about how a bond can have polarity because the two elements that are sharing the electrons are not sharing them equally. And as a result, the electrons spend more time with the more highly electronegative element, giving that bond a polarity. So one end would be partially positive and one end would be partially negative. What we're going to talk about now is the entire molecule and its polarity. And what happens is, if a molecule has polarity, it's because there is a charge across the molecule. So molecules that have nonpolar bonds, those where the electronegativity is the same at either end of the bond, will not have a polar molecule. Since there is no charge to the bonds, there will be no charge to the molecule. So when we talk about polar molecules, they are never going to be our diatomic molecules. Iodine, fluorine, oxygen, nitrogen, all of those will be nonpolar molecules. So let's look at one of the molecules that may have polarity because the bonds themselves may be polar. We're going to talk about water. So water has hydrogen, which has one valence electron, and oxygen, which has 6 valence electrons. Hydrogen can make one bond because it has one unpaired electron, and oxygen can make two because it has two unpaired electrons. So the resulting molecule will have oxygen with its two pairs of molecules on the outside, and then a hydrogen here and a hydrogen here. What we should do at this point is look up the electronegativities of hydrogen and oxygen to see which one is higher. I don't need to do that since I know that oxygen is a lot closer to fluorine. If you're ever worried you don't know which one might be higher, you can look it up in Table S. I'm not going to do that right now. I don't feel I need to. I know oxygen is higher. Hydrogen's about 2.2 and oxygen's in the 3s somewhere. So the electrons are actually going to spend more time with oxygen than they do with hydrogen, leaving this end of the bond partially positive. And especially with hydrogen, you're going to be exposing the proton because the only electron that hydrogen has is now spending more of its time with oxygen. This end then would be slightly negative. And as a result, when we look at this whole molecule, this end of the molecule is positive and this end of the molecule is negative, creating a dipole or a polarization of that molecule. Let's look at ammonia next. Ammonia is NH3. Nitrogen has 5 valence electrons. And again, hydrogen has 1. So that means that nitrogen will make 1, 2, 3 bonds, and hydrogen will make just 1. That is why we have 3 hydrogen atoms for every nitrogen atom in a molecule of ammonia. So it looks like this. Once again, you should look up the electronegativities, but I know that nitrogen is higher than hydrogen. So once again, the electrons are going to spend more time with nitrogen, leaving this end of the molecule positive and this end of the molecule negative. So it would be a polar molecule. It has polarity to the molecule. Let's look at another one here. We've learned that carbon will move its electrons so that it can make 4 bonds because otherwise it would not be able to get its full octet. Hydrogen, again, can only make 1, so we're going to end up with a molecule that looks like this. Carbon's electronegativity is about, I think, 2.6. Hydrogen is 2.2, so again, the electrons are going to spend more time with carbon over hydrogen. But what's going to happen this time is it's carbon that will be slightly negative as a result, and on the outside of this molecule, everywhere you look, it's positive. So there's no second pole to this molecule. It's only positive on the outside. You're not having a charge across the whole molecule like you see in water, where this whole end is positive and this end is negative, or with ammonia where this side is all positive and this is negative. So essentially what we see is that if there's any symmetry to the molecule, the polarity of the bonds are going to cancel each other out. So essentially, the first thing you need to identify molecule polarity is, are the bonds themselves polar? Which in all of these cases, they are polar since they're between two different elements with different electronegativity. Then you need to look at the symmetry of the molecule. For these two, the molecules are not symmetrical. If you were to cut it in this direction and this direction, it's not the same on both sides of your line. This one might be the same on either side in that direction, but it's not in this direction. Where with methane, or CH4, it is the same in both directions. So if it's symmetrical, the bond polarities kind of cancel each other out, making the molecule nonpolar. So let's label these so we don't forget. This one was polar. This one was polar. This one is nonpolar. The charges cancel out when the arrows are opposite each other, making the molecule nonpolar. So that's one way to look at it. This arrow is opposite this one. They cancel each other out. This arrow is opposite this one. They cancel each other out. If all the arrows cancel out, it's nonpolar. This arrow cancels out this one, but there's nothing to cancel out this one, leaving this one polar. This arrow does not have an arrow opposite to cancel it, nor does this one have anything opposite to cancel it. So it's polar. In fact, water is an incredibly polar molecule, and we'll talk about that a bit more later on. So let's look at some of the possibilities for arrows you might see. If you had arrows over bonds, each going like this, it would still be nonpolar. If you had arrows, again, each going out like this, it would be nonpolar. And then, like the example we just had, if they're all facing in and they all cancel, it's nonpolar. It'd also be nonpolar if they were all facing out in the same shape. So here's an example where it would be nonpolar. That's the kind of nonpolar molecule that carbon dioxide is. Here's another one that would be nonpolar. In that case, the atom in the center would have to have a higher electronegativity. This is like the example we did right here, where they're all facing in toward carbon. But you could have a similar thing when we have fluorine on the outside, but then your arrows would be facing out. But they're all canceling each other out, making the molecule nonpolar. Some polar examples, you might see an example where there's only one bond that's polar, like you might see that in something like HF. There's only one bond and it's relatively polar. You might see it like we just saw with ammonia, where you have two bonds that cancel each other out, but not that third one. That will make it polar as well. So essentially, if a molecule is symmetrical, it will be nonpolar. But if it is non-symmetrical, like these two examples over here, it's going to be polar. So let's look at some of these. This is actually the shape of water. It's just twisted a bit, facing the other way. That we call a bent molecule. It will always be polar. This is a linear molecule, And this one, it kind of depends. If it's between two different elements, like this seems to be depicting, then it'll be polar. But if it's like H and H in hydrogen, then it's going to be nonpolar. So it really depends on if the bond is polar. If the bond is polar, this molecule will be polar. If the bond is nonpolar, because it's one of our diatomics, like H2 or N2 or O2, then this would make it so that it was polar molecule. And then this last one, we call this tetrahedron. Although it's difficult to tell in the way this one is drawn, this one is symmetrical. A tetrahedron always is, and typically it involves carbon, and it will be nonpolar. For the bent molecule and the tetrahedron, you can always say the polarity of the molecule, where with a linear molecule, it depends on if it's between two atoms of the same element. If it's two atoms of the same, like this one, that would be nonpolar. But if it's two different elements, like H and F, then it would be polar. All right. Now the next thing, and this will become important, we say like dissolves like. Just like in biology, you guys learned that shape determines function, and that's a phrase that you should memorize and remember for any biology course you ever take. Like dissolves like will help you a lot in chemistry like that. Polar molecules will dissolve in polar liquids. Nonpolar molecules will dissolve in nonpolar liquids. So I have a stupid little joke for you that will now make sense. All right, here's some practice and drawing. We're going to draw in on all of these the bond polarity, and when we're done, we're going to determine if each of them has a molecular polarity. So I'm going to go ahead and I've already done NH3 with you today, so I'm going to do HCl as kind of an additional reminder. First thing you want to do is look up the valence number for each element. Hydrogen is 1, chlorine is 7, and again, you don't have to use the X's and the dots. I just like to show where the electrons come from. It's more helpful with ionic bonding. Hydrogen has 1 valence electron, therefore can make 1 bond. Chlorine has 1 unpaired valence electron and therefore can make 1 bond. I'm just going to rotate those electrons a bit to make them line up. So essentially this is going to move down to this side. And when it does, it's going to share with the unpaired electron on chlorine in order to make a bond like this. So that line actually represents the 2 electrons, the one that's shared from hydrogen and the other that's shared from chlorine. The next step is to look up their electronegativities in table S, and you're going to find when you do that chlorine's electronegativity is much higher than hydrogen's. So we're going to point at the one with the higher electronegativity. So that has a bond polarity. They don't have the same electronegativity, so there's a bond polarity. Once we have our drawing, now we can sort of determine whether or not it has molecular polarity. Is this molecule symmetrical? And the answer is no. It's not the same on either side. So that will make this molecule polar, and it will dissolve in other polar substances. What you should do now is pause this and go ahead and try the other ones. And once you've tried drawing the other ones, determine the molecule polarity. All right, here's the first 4 completed. The bonds in ammonia are polar, and because these two cancel each other out, but this one doesn't have anything to cancel it out, the molecule itself is polar. Iodine, the bond is nonpolar. The electrons are being shared entirely equally between the two iodines, so it is going to be a nonpolar bond. Therefore, the molecule itself must also be nonpolar. H2S, the bonds are polar, albeit slightly polar. They don't cancel each other out. They aren't opposite each other. If there was one going this way, that would cancel it out like these do. But they don't have anything to cancel them out, making the molecule itself polar. Now we're looking at the bottom four. These are kind of tricky. They did all end up being nonpolar. Silicon, being directly below carbon, also has 4 valence electrons, and it will also move its valence electrons to maximize its bonding. Otherwise, it cannot succeed in getting its full octet. So when it does that, it can make a bond on each side, and that's what it does with hydrogen, much like carbon does. Because the bonds are polar, but they're opposite each other, they cancel each other out, making the whole molecule nonpolar. It is symmetrical. Oxygen wants to make 2 bonds. Being that it can only make those 2 bonds with one other oxygen atom, the 2 electrons that are unpaired sit next to each other on one side so they can share, creating a double bond. But that double bond is between 2 atoms of the same element. There's no polarity to the bond, therefore the molecule is also nonpolar. Carbon dioxide is very tricky, and I said in previous notes on covalent bonding that you should probably just memorize what it looks like. Carbon has to make 4 bonds. Oxygen can only make 2. So once again, oxygen's going to move them so it can create a double bond, much like it did in O2, but it's going to do that on either side of carbon. So you're actually creating 2 polar bonds, but because of the molecule's symmetry, it does cancel out. These 2 cancel each other out, making the molecule nonpolar. The last one, fluorine, only has 1 unpaired electron. It'll make 1 bond with the other fluorine atom. This bond itself is nonpolar because it's between 2 atoms of the same element, making that molecule, and I neglected to write this down, nonpolar. And that's how you figure out molecule polarity.